Good morning, everyone. In today's class, we are going to understand how electric vehicle components are named, labeled, and represented in industry. This is extremely important because EV data sheets, service manuals, safety documents, and research papers all use standardized nomenclature. When you look at an EV spec sheet, you'll see terms like pack voltage, cell chemistry, PMSM, inverter rating, and many more. Without understanding this nomenclature, interpreting EV component specifications becomes difficult. EV battery nomenclature follows a very systematic approach. When you see a label like 96 seconds 3P NMC battery pack, each element has a precise meaning. The S stands for series connection and P stands for parallel connection. So 96 seconds means 96 cells connected in series, and 3P means 3 identical strings connected in parallel. This arrangement determines the final voltage and capacity of the pack. You'll also notice battery chemistries like LFP, NMC, NCA, and LMO. LFP, lithium iron phosphate, is very safe and has long cycle life. NMC, nickel manganese cobalt, offers high energy density for good range. NCA, nickel cobalt aluminium, is used in high performance packs, like in many Tesla vehicles. Each chemistry targets a different balance of safety, cost, and energy. Next, let's look at voltage ratings. You may see a battery labeled as a 350 volt pack, 400 volt, or even 800 volt architecture. This indicates the operating class, not the exact voltage, which varies with the state of charge. Data sheets usually provide nominal, minimum, and maximum voltages. Battery capacity is given in kilowatt hours, for example. A 50 kWh pack can deliver 50 kilowatts for 1 hour, which affects driving range. Another key term is the C rate, like 0.5 degrees Celsius, 1 degree Celsius, or 3 degrees Celsius. A 1 degree Celsius rate means full charge or discharge in 1 hour, 2 degrees Celsius in half an hour. C rate tells us how fast a battery can safely deliver or receive energy. C rate is the ratio of charge or discharge current to battery capacity, acting as a universal speedometer for energy flow. 1 degree Celsius fills or empties a pack in 1 hour, 0.5 degrees Celsius in 2 hours, 2 degrees Celsius in 30 minutes, and 3 degrees Celsius in 20 minutes. This dimensionless figure lets engineers, drivers, and fleet managers instantly compare charging speed, acceleration punch, and thermal load across any EV chemistry or size without decoding ampere or kilowatt figures. The basic formula for a charging or discharging current equals the C rate times the battery capacity in ampere hours. For example, a 60% ampere hour battery at 1 degree Celsius charges or discharges at 60 amps, at 2 degrees Celsius it's 120 amps, and at 0.5 degrees Celsius it's 30 amps. This helps us understand how fast a battery can safely charge or deliver power. Charging at 0.2 degrees Celsius to 0.5 degrees Celsius is considered slow charging. It's very gentle on the battery, generates minimal heat, and maximizes cycle life. This is typically used for home AC charging, like level 1 or level 2 chargers. In practical EV terms, this is where the battery is happiest. Overnight home charging usually falls between 0.3 degrees Celsius and 0.5 degrees Celsius, depending on the charger and battery size. A 1C rate represents standard charging or normal discharge. It's a moderate rate, producing acceptable heat while balancing charging time and battery health. Many EV batteries and their BMs are designed to safely handle 1 degree Celsius during everyday driving. Some fast AC or DC chargers also operate close to this rate for convenient yet safe charging. A 2C rate corresponds to fast discharge or moderately fast charging. It draws significant current and generates more heat. During rapid acceleration, steep climbs, or regenerative braking, the battery may momentarily discharge at 2 degrees Celsius. Some premium EVs with liquid cooling and advanced thermal management can even handle 2 degrees Celsius fast charging at DC fast chargers safely. Charging or discharging at 3 degrees Celsius and above puts very high stress on the battery and requires excellent cooling. Frequent use can reduce battery life, so only high-performance EVs typically support these rates. In real-world EV use, Extreme acceleration in performance vehicles may draw 3 degrees Celsius to 5 degrees Celsius discharge. Similarly, ultra-fast DC chargers, such as 350 kilowatt stations, can push charging close to 3 degrees Celsius for short periods, depending on the battery chemistry. Different battery chemistries have different safe C-rate limits. NMC, used in most cars, typically allows 0.7 degrees Celsius to 1 degree Celsius, offering a good balance and fast charging capability. LFP, found in vehicles like Tesla and BYD, can safely handle 1 degree Celsius to 2 degrees Celsius, giving excellent longevity and tolerating higher C rates. Lithium titanate, or LTO, is rare and expensive but supports ultra-fast charging at 5 degrees Celsius to 10 degrees Celsius, making it suitable for specialized applications. Higher C rate linearly shortens charging time. A 75 kilowatt-hour pack needs 1 hour at 1 degree Celsius, 30 minutes at 2 degrees Celsius, 20 minutes at 3 degrees Celsius, assuming constant power and no taper. Real-world curves flatten above 80% SUC, yet peak C still defines road trip stop length. Infrastructure planners size charger current and cable cross-sections to deliver the advertised C rate, while drivers choose charging stations based on the implied minutes to 80 displayed on navigation screens. In the context of EVs, implied minutes to 80 refers to the estimated time it would take to charge a battery from its current state of charge, SOC, up to 80% based on the current charging rate. Peak discharge C rate translates directly to wheel power. A 3C pulse from a 75 kilowatt-hour pack releases 225 kilowatt, enabling sub-5 second 0 to 100 km per hour launches. Motor controllers and inverters must handle the resultant 400 to 800 amps without voltage sag, while BMS monitors cell temperature and voltage dip to prevent plating. Sustained high C-rate discharge is rare. Typical duty cycles last only seconds, but the capability differentiates, performance trims, and justifies larger cable and fuse budgets. Elevated current magnifies heat and mechanical stress, accelerating capacity fade and impedance rise. Lithium plating above 1 degree Celsius in cold NMC cells can slash cycle life by 30%, while repeated 3 degrees Celsius charges raise swelling pressure inside prismatic housings. BMS counters with temperature floors, SOC windows, and current taper algorithms, but physics imposes a durability tax. Fleet operators must weigh faster turnaround against earlier pack replacement, influencing warranty terms and residual value forecasts. Doubling C-rate quadruples internal heat, forcing liquid cooling loops, cold plates and chillers sized for peak load. Coolant flow rate, inlet temperature and cell spacing are calculated from maximum sustained current, ensuring no cell exceeds 40 degrees Celsius during a 3 degrees Celsius charge in 45 degrees Celsius ambient. Higher C targets also demand thicker bus bars, lower resistance contacts, and real-time thermal sensors that feed back into BMS derate logic, directly impacting pack mass, volume, and cost. Choose C rate by duty cycle, overnight 0.3 degrees Celsius, public fast 1 to 2 C, ultra fast corridor 3 degrees Celsius with validated cooling. Verify chemistry specs, enforce temperature floors above 10 degrees Celsius, limit SOC window to 10 to 80% for high C events, and match connector and cable ampacity. Balance energy density against cycle life cost, document derate curves for warranty, and confirm charger output aligns with cell capability to avoid plating, swelling, or premature capacity loss in field operation. Practice real decisions. Compute charge time for a 120 ampere-hour LFP pack at 1.5 degrees Celsius. Select the minimum C rate to add 100 kilometer range in 10 minutes, and identify the faulty claim when a vendor advertises 5 degrees Celsius charging at 10 degrees Celsius without preheat. These 3 exercises cement numeric fluency, prepare engineers for audit questions, and give procurement teams confidence to challenge inflated specifications before signing supply contracts or releasing vehicles to customers. Finally, battery packs often list IP ratings, like IP67 or IP69K. IP stands for ingress protection. The first digit tells us how well the battery is protected against dust, and the second digit indicates water protection. For example, IP67 means the battery is fully dustproof and can survive temporary immersion in water. These ratings help engineers quickly understand the safety, durability, and compatibility of battery packs. These nomenclature elements help engineers instantly understand safety, performance, and compatibility of battery packs. Everyday IP levels are IP54 to IP55, which are street-friendly shield. IP54 grants dust-protected status and splash resistance, adequate for external displays and basic enclosures that never face pressurized water. IP55 adds defense against low-pressure jets, suiting charging plug housings, sensor pods, and cooling fans mounted outside the cabin. Neither rating seals completely against dust, so drivetrain and energy storage parts demand tougher specs, while these economical codes keep non-critical peripherals safe during routine rain and washdowns. Mid-range IP grades IP65 are dust-tight low-pressure guard. IP65 delivers full dust exclusion plus survivability under low-pressure water jets from any angle. Inside EVs, this rating is targeted at motor controllers, onboard chargers, and DC-DC converters positioned beneath body panels where road spray and cleaning hoses are likely. The gasket-level seal prevents conductive dust from reaching high-voltage traces, extending service life while allowing flexible exterior mounting without additional shielding, thus trimming weight and cost. IP66 is a powerful jet road warrior grade rating. IP66 equals IP65's dust tightness, but withstands powerful water jets, making it the minimum for underbody devices, wheel well electronics, and compact chargers on two-wheelers that endure direct spray from puddles and pressure washers. The stronger seal keeps water away from sensitive power stages, yet the housing remains lighter than immersion-rated enclosures, striking a practical balance between environmental protection, thermal dissipation, and packaging efficiency for cost-sensitive platforms. IP67 are immersion-rated and temporary submersion standard rating. IP67 certifies complete dust blockade and safe immersion to 1 meter for 30 minutes, the de facto benchmark for EV battery packs, inverters, connectors, and motors. The spec covers flooded streets, monsoon gutters, and high-pressure cleaning without extra covers. By validating that seals survive modest hydrostatic pressure, OEMs assure customers of post-flood drivability and protect high-voltage insulation, reducing warranty risk in regions prone to seasonal waterlogging. IP68 level are premium deep dive rating for EVs. IP68 keeps devices fully dustproof while allowing continuous water submersion, with the exact depth and time set by the manufacturer. Premium SUVs, off-road vehicles, and marine-friendly EVs use this for batteries, motors, and power electronics to handle river crossings, beach launches, or submerged parking. Thicker housings, potting, and stronger connectors add cost, but provide reliability in extreme conditions and improve resale value. IP69K is an ultimate high-pressure survivor rating. IP69K is the highest protection rating, combining full dust tightness with resistance to very high-pressure hot water jets. It's designed for the toughest cleaning conditions, like rotating washes used on buses, trucks, agricultural EVs, and industrial fast-charge connectors. Special seals, stainless interfaces, and drainage channels prevent water from reaching high-voltage parts, keeping the vehicle safe, reliable, and compliant with regulations. A single table can show dust and water protection alongside typical EV applications. For example, IP54 is good for displays, IP55 for external sensors, IP65 for chargers, IP66 for underbody components, IP67 for batteries and motors, IP68 for off-road packs, and IP69K for commercial or agricultural vehicles. This quick reference helps designers choose the right protection based on environment, cost, weight, and thermal needs, without going through long datasheets. Proper IP ratings prevent water from causing short circuits in high voltage systems, reduce corrosion that can make the battery heat up, and keep insulation safe during floods or rainy rides. Sealed enclosures also stop dust from reaching control boards, which avoids damage to components. Choosing the right rating from the start helps engineers reduce failures, protect passengers and first responders, and avoid expensive recalls. Consistent sealing blocks moisture that swells conformal coatings and salt that erodes solder joints, extending inverter and battery life beyond 10-year warranties. Dust exclusion maintains cooling fin efficiency and connector spring force, stabilizing thermal management and high current interfaces. The resulting drop in intermittent faults translates to higher vehicle uptime, lower service visits, and stronger brand reputation, justifying the marginal material cost of upgraded gaskets and O-rings. High IP ratings make liquid cooling safe for EV batteries and motors. Because the housings are sealed, water sprays or road splash cannot disturb the coolant loop. That means engineers can push more current and heat through cells without adding air vents or big fans. It also protects the coolant during floods, so dirty water can't mix in and cause insulation failure or safety issues after a submersion event. Match the IP rating to the worst-case scenario. Pressurized washing needs IP65 or higher. Temporary flooding requires IP67. River crossings or deep puddles call for IP68. And steam cleaning demands IP69K. It's important to balance weight, cost, and thermal performance. Overspecifying adds unnecessary mass and expense. Also, check that gaskets work with coolants and salts, ensure proper drainage, and confirm cable glands maintain the same IP to avoid weak points in the sealed system. Fly what you learned. Identify the correct IP code for an underbody charger facing road spray. Choose the minimum rating for a battery submerged in 80 centimeters of water for 20 minutes. And spot the error when a vendor claims IP54 for a commercial bus steam wash daily. These three scenarios reinforce decision rules, prepare certification engineers for audit questions, and give procurement teams confidence to challenge non-compliant suppliers before hardware is locked into vehicle programs. When you read a power electronics data sheet, the first term you will see is rated power, written in kilowatt, for example, inverter 150 kilowatt peak, 80 kilowatt continuous. This two-power rating system is used because EV inverters can supply high power for short bursts, but their continuous capability is lower. The continuous rating guides us in design of thermal system, motor matching and cooling while preventing semiconductor overheating during sustained highway load. Another important term is switching frequency, usually written as 10 kHz, 16 kHz, 20 kHz. This tells us how fast the inverter switches the current flow using power semiconductor devices like IGBTs or MOSFETs. The onboard charger has terms such as OBC minus 3.3 kilowatt, OBC 7.2 kilowatt, or OBC 11 kilowatt. These numbers indicate how quickly the EV can charge from an AC source. Another common nomenclature is converter ratio in the DC-DC converter. It is written as high voltage to low voltage, HVLV. For example, 405 to 12.5 DC-DC converter. Now let's look at electric motor names in EV spec sheets. The first thing you'll notice is the motor type. PMSM means permanent magnet synchronous motor and is very efficient, especially at low speeds. IM means induction motor and works using electromagnetic induction instead of magnets. SRM is switch reluctance motor with a simple, cheap rotor design. BLDC means brushless DC motor. Each type tells us how the motor is built and how it performs. Next is torque rating, written as continuous torque and peak torque. Peak torque is available for a few seconds for acceleration, whereas continuous torque can be sustained without overheating. You will also see base speed and maximum speed listed in RPM. Base speed is where the motor transitions from constant torque region to constant power region. Motor naming also shows the cooling type: air-cooled, liquid-cooled, or oil-cooled. Cooling decides how much power the motor can safely handle. You may also see a kV rating in small EVs. kV means RPM per volt. So a 120 kV motor spins at about 120 revolutions per minute for every volt you feed it. This number helps you pick the right motor for your target vehicle speed. In EVs, driveline terms are fewer but still useful. The key one is the reduction ratio. Numbers like 9.7 to -1 tell us how many motor revolutions equal one wheel turn. Because motors spin very fast, this gearing boosts wheel torque. You'll also see drive layouts like FWD, RWD, and AWD, which simply show which wheels receive power. The last component set involves safety and communication nomenclature. You will find terms like HVL, which stands for High Voltage Interlock Loop. It is a safety circuit that ensures the high voltage system is disconnected when connectors are opened. Then we have CAN, CAN-FD, LIN, and Ethernet, which refer to communication protocols used to coordinate various EV components. Battery and motor controllers are labeled as VCU, or Vehicle Control Unit. Similarly, the BMS refers to the battery management system. Final takeaway: once you can decode the codes, the data stops looking mysterious. Reading cell chemistry, power and torque ratings, IP levels, and communication labels helps you compare parts quickly and avoid design mistakes. It means fewer mismatches between battery, inverter, motor, and controllers, and faster decisions when selecting EV components. To conclude, EV nomenclature is a standardized language that helps engineers interpret component behavior, compatibility, and performance. By understanding the naming system for the battery pack, power electronics, motors, driveline, and safety systems, you will be able to read EV datasheets and design documents accurately. Thank you, and we will meet again in another topic on EV powertrains.